Of Astro 101. So, I'm going to quickly answer a question that not a question, but a statement. Oh, let's mute that. So, I did see someone just mention that I went on vacation, which it was kind of like a vacation. I went to the Planetary Science Institute's annual retreat, and so had a good time there. Shared the work that I'm currently working on. As Andre stated, we're currently doing an analysis, and we've had these discussions in the past. Incidence angle, basically trying to see exactly how the angle at which sunlight hits the lunar surface, how it's affecting our moon mapper users' ability to be able to identify craters. But I'm not going to get into that today. Hey guys, hey Guido, hey Paranor. So yes, as Larry put it, we're talking about Cephied variables. Hey Finring. And so, yes, oh, it's nap time for you? Alright, well then we'll see you later, Paranor. Hey Susie. Hey Uncle Bill. And so, yeah, today we're going to be talking about Cepheid variables. I was trying to come up with a bunch of different things that we could talk about, and there's plenty of topics in astronomy. And this one is the one thing that I know I have not talked about yet. Definitely had a good time at the retreat. It was quite nice. It was relaxing. But I'm actually happy to be back at work. So, as you can notice, though, for today, I'm by myself. Joe is unable to join us. He's going to be busy with some other CosmoQuest colleagues and doing some programming stuff, things that I know very little about. So, he's busy doing that. We're going to go ahead and rock on with talking about Cepheid variables. So, this image that I'm showing in the background here, is actually a Cepheid variable that's located within the Milky Way galaxy. If I'm remembering the correct name for it, it's called RS. Well, for short, it's RS Pup, which I think is short for RS Puppis. So if you did a search on it, you could be able to find it. But we're talking about how these Cepheid variables, these variable stars, are great ways of being able to identify distance from us to wherever the star is located. So what letter is Cepheid variable in the class of? So this a Cepheid variable is actually a giant star. Um, it's not. It's actually not a main sequence star. So those classifications are for main sequence stars. The OBAFGKM, which another nice and neat like acronym or mnemonic device you can use for that is the one I learned at least is OB a fine girl kiss me. So, but yeah, that's the stellar classifications for main sequence stars. This is actually a red giant star, or a giant star. I don't want to say red giant. It's a giant star. But we're gonna go ahead and talk about these particular stars and how they're used to be able to determine distances. So first thing, of course, is talking about, well, what is a standard candle, right? Um, so here I'm showing, of course, a candle, and the idea here is that if you could take some sort of detector and measure the amount of energy that this candle puts out over time, you'd essentially have its luminosity. And if you could be able to measure how the luminosity either stays the same or changes over time, and you notice this to be a trend for every single candle that's exactly like the one I'm showing here, then you'd have essentially a standard candle. The key takeaway point is that you know its luminosity. You know how its luminosity acts over time. And so, with these Cepheid variables, we've been able to determine, and it's some time ago, we've been able to determine that we can use these Cepheid variables to be able to, we can use them as standard candles. So, some observations of Cepheid variables in the past. Here I'm showing a Hubble Space Telescope image of course, what it's showing here is Cepheid variable star V1 and M31. And so basically we're looking at a Cepheid variable star in another galaxy. So this M31 is the Messier 31 object, and it corresponds to the Andromeda galaxy. So this is a single star, its light being observed in an entire another galaxy. And what they're showing here basically is that over time, if you look at the timestamps in the four subframes here within the image, you can tell that from over the course of roughly December 17th to like January 26th, so over the time scale of roughly like a month, a little bit over a month, we're kind of seeing the star doing something. It's increasing in brightness over this time period. And one of the questions that you might ask is, well, why is it increasing in brightness? And another thing to note, of course, is that this is the reason why it's variable. It's variable because of the fact that its brightness increases over time. With other stars, like for example, main sequence stars, their brightness doesn't really increase that much over time. Very, very little. But in this case, on a time scale of a few weeks, we can see changes in brightness. So what's physically happening with this variable star system? So here I have a nice little quick animation to kind of give an idea of what's going on. I'm not going to go too deep into the dynamics that's occurring within the interior, but essentially, over time, we kind of see with these Cepheid variables that at one point in time they're at one brightness, and at another point in time they're at a different brightness. And these changes in brightness are primarily due to the internal structure of these stars. This internal structure allows for the star to be able to undergo this increase in brightness, and the reason why it's increasing in brightness is because of changes in its changes in its temperature and its physical size. So you can actually use Stephen Boltzmann's law to be able to better understand this the effect that's going on here. And so, if you were to point a detector at one of these objects, these Cepheid variables, you'd essentially see a light curve that looks like this. So along the y-axis, so we have brightness, which is apparent brightness. It's not its absolute brightness. It's basically how bright it appears in the sky to us, versus the time over which you're observing the Cepheid. And so what you'd notice is that initially, when it's going from its dimmest to its brightest, it undergoes a really quick change in brightness. And so basically its physical size, while dimmest is small, then it gets really big, and when it starts at its biggest size, it's at its brightest. And then over time, it'll slowly decay back down. That is, its brightness will decay back down to its dimmest point, which also corresponds to when it's smallest. And then again it will rapidly rise back up to when it's at its brightest. Well, given the nature of this sort of pulsation of the star itself, changing in physical size, it produces this change in brightness, and you can actually measure how long it takes to undergo from one bright peak to another bright peak, or from one dim valley to another dim valley. And so what you establish here is something known as a period luminosity relationship. Now, of course, what we're measuring here is not actually the luminosity of the star. I should note that. This brightness is the apparent magnitude of the star. However, there is a technique of getting to its absolute magnitude, or its luminosity. And so we're going to talk about that now with this very next slide. But I'm going to take a moment to quickly look at comments, because I'm pretty sure I'm missing stuff. So I quickly see that Larry states helium burns and then stops, right? So once the star leaves the main sequence, it's no longer burning hydrogen to helium in its core. And it's, for the most part, it has a helium core surrounded by a hydrogen shell. And so at this moment in time, it's no longer burning hydrogen in its core. Now, whether or not it's burning helium is a whole other situation. Some stars will go on to go ahead and continuously burn helium to get higher elements. to kind of stave off from, you know, dying, essentially becoming a dead star. And this heavily depends on the mass of the initial main sequence star that's now undergoing the dying process. Can you imagine being on a planet around a star that is so variable? Um, so that's a very good question. I'd be kind of scared, right? Because these Cepheid variables, the fact that they're undergoing this change in brightness is due to the fact that they're undergoing a change in size. So if you're a planet nearby one of these things, I'd be kind of worried about it being consumed, you know, during one of those phases in which it's growing bigger. But if you're kind of far away off, nevertheless, the increase in brightness is worrisome, right? Because that can also indicates an increase in temperature. So it's that's a great question. It's kind of hard for me to get to a definite answer for it. So will our sun get to this phase? And I believe the answer for this is no. So if you were to do a Google search for Cepheid variables, what you'd find is that they lie. If you look at an HR diagram, they lie within the instability strip. So with the HR diagram, you have essentially luminosity along the y-axis and temperature along the x-axis. And within the plot, you kind of see, well, depending on the orientation of the x-axis, whether you're going from, as you move from right to left along the x-axis, if you're going from coolest to hottest, you will see a diagonal line running from the upper left-hand corner to the lower right-hand corner. And that line, essentially, of stars corresponds to the main sequence. Upper right of that plot, you kind of see your giants. And this is kind of the area in which I'm talking about here. So, perpendicular to your main sequence, so I'm going to try my best to do this. I wish I had like two pens next to me. But perpendicular to your main sequence, right? You kind of have this little line which corresponds to the instability strip. Um, and you basically find these variable stars there. So as far as our sun's concerned, I don't believe it'll pass through the instability strip. So I don't think we have to worry about this sort of phenomena happening with the red giant form of our sun. But yeah, so what we end up finding out with these Cepheid variables are that you can establish this period luminosity relationship. One, but two, there seems to be kind of two populations of these Cepheid variables. And you see them here in the graph as type 1 or population 1 Cepheids versus type 2 or population 2 Cepheids. The key thing here, I believe, is that if you were to do a vertical line through each of these curves here, you'd notice that, of course, you'd get a single period, but you'd have to determine, well, I'm looking at a Cepheid. I've measured a period for its change in brightness. However, which population of Cepheids does it belong to? And I believe the way in which you'd be able to determine it is by looking at the... Now, going back to what someone said earlier, the spectral type, essentially, of the star. And basically, what spectral type means is that you're looking at the composition of elements that are within the atmosphere of the star. And what you'd notice, though, is that the a Cepheid 1 variable star at, let's say, period A, will have a different spectral type for a Cepheid variable star that's at the same period, but that's in a different population. All right. And so with that said, I normally would say I'm done here, but actually I wanted to be able to see exactly or test how well does this method work in being able to determine distances. And I just realized I didn't even talk about how exactly you get the distance from this. So all right. So what you do is this. Of course, I'm gonna go back one slide. So of course you can measure the apparent brightness of the Cepheid star, as seen here, right along the y-axis. I believe what you'd want to do is go ahead and take an average brightness for the star itself. One, and then two, you'd want to be able to, of course, measure the period of these oscillations in brightness. Now, with the average magnitude of the star, um, you know its apparent magnitude, one, from that. However, you want to be able to determine the distance from it. Well, there's a nice little formula that we've talked about in the past, for being able to determine distances from stars when you're concerned with the magnitude of the star, and that's known as a distance modulus. If you want, you can go ahead and you can look at the Wikipedia article for that. Just type in distance modulus into Google, and it'll like pop up probably as like the first result. But basically, the distance modulus relates the apparent magnitude or brightness of a star to its absolute magnitude or luminosity of the star, given the fact that all of this, those two quantities, are determined by the physical distance between us and the star itself. Um, so going back to this plot, now I'm gonna try my best to kind of like set this up such that if you look at the x-axis, this axis is in units of time or days. This axis is in unit of period. And so basically, what's happening as far as the x-axis is concerned, what you can do is you can use some what I've now come to know as like fairly complicated math. It's not so complicated now once you get used to it, but you can use what's known as a Fourier transform, and you can extract from for example, from plots like this that are essentially a time series of information. You can extract from that information like periods or frequencies, and you can produce a axis that's in units of that basically gives the period of an object. But basically, we see period along the x-axis here, which is still in units of time, um, and it's against the y-axis, which is luminosity. Now, luminosity is not the same thing as brightness. Going back to our previous one, the only way you can convert the brightness or the apparent magnitude of an object to its corresponding luminosity or absolute magnitude is if you know the distance. And so the way in which we were able to construct this plot, this luminosity period luminosity relationship, is by one, taking stars within our own galaxy, of course, Cephied variables, that is, within our own galaxy, and measure and producing plots like this one, where we can measure the brightness over time. And then for a single star, we determine its period, one. We determine its average brightness, two. But then we need to know its distance to get an absolute magnitude. Well, given that it's within our galaxy, we can use other distance measurements as being able to kind of build the plot we see here. And typically, I think you'd end up using parallax to be able to determine the distance to the star. And with that distance and the apparent magnitude of the Cepheid variable, you can establish the absolute magnitude, which essentially is the same thing as the luminosity of the star. And you'd build a graph like the one we see here of a bunch of Cepheids to be able to establish the relationship that we're seeing in this plot here. Take a moment because I've been talking for a moment and I need to stop and look at comments here. Yes. So I think what Larry is saying here is, the variability in the star is not due to fusion. That's what I said earlier, that's not what I meant. Um, the variability in the star is due to the brightness in the star is due to the fact that it's undergoing changes in size, and this is all because of the internal structure of the star, not so much associated with fusion, but with the distribution I think of the distribution of the helium within the star in particular. Um, but what I wanted to get to, and I'm not seeing anything else here. Not seeing anything else here. What I wanted to get to though is a calculation. So I brought up the fact that we have this Cepheid variable. I'm going to go back a few slides. We have this Cepheid variable star V1. This is an actual like name for a star, and I think that the V1 means variable 1 in M31. And so I was curious to kind of see exactly what would be the distance measurement to this Cepheid variable in M31. Now M31, which is the Andromeda galaxy, is stated to have a physical distance from us of I think it's somewhere around 780 kiloparsecs. So what I'm going to do now is we're going to go ahead and switch. I'm going to switch we're going to go ahead and switch this topic screen to something else, so we can look at the quick calculation I made. Now, guys, I'm going to let you know that the calculation I made was like, and this is true for almost all of the calculations I make, it's like done like minutes before the stream. So I was actually quite happy with this calculation. I mean, it's on the same order of magnitude, but this to kind of walk through the steps of what one would do to be able to determine the distance to one of these stars. So let's do that. We're going to change that. We're going to move that up so we can see it better. And we're going to kind of adjust it. That way it looks a little bit better than what it is. Alright. Boom. And lastly, alright, there we go. So, again, quick calculation for being able to determine the distance to this particular star, Cepheid star, imaged, I believe, by the Hubble Space. Well, it has been imaged by the Hubble Space Telescope. But if I'm not mistaken, this was one of the very first Cepheid stars observed, and it was observed by Hubble himself. So let's see, where is that document? Right here. So the problem that I've kind of set up here, given the information I've been able to obtain on this Cepheid variable, is that we have been given the observations of a particular population 1 star, which I've told you the particular star. And you can always just look up you can look up that information just by typing in Cepheid variable star V1, and I'm pretty sure you'll find a Wikipedia article on it. The information I have here, though, I've gotten from 2 papers. So population 1 Cepheid variable has a period of 31.4 days and apparent V-band magnitude of 19.4. And it's from that paper that I was able to get this information. So we're basically going to use this information in this plot that I'm showing here, that I got from another paper, quoted here, to be able to determine the distance to this star. Now, of course, in this situation, I've already went ahead and given the two key things that we need. We need the period of the star, and we need to know what its apparent magnitude is. And so, with this information, we first take the period, and we'd use the period luminosity relationship to determine the absolute magnitude of the star. And someone a very long time ago in 1996 determined that, and I believe this is primarily for population 1 Cepheids, this curve here, that the relationship exhibits this mathematical formula. The absolute magnitude in V-band is equal to negative 2.76 and so forth, where the period has to be in units of days. So basically, we're just going to plug and chug our 31.4 days period into this equation, and what we get, essentially, is a V-band absolute magnitude of negative 5.5. Now, going from there, we end up using the distance modulus, and again, you can look at Wikipedia for the various equations they have for the distance modulus. This is one um, form of that equation where the distance has been solved for, and it's a function of the apparent magnitude, which is the lowercase m, and the absolute magnitude, which is the capital M. So plugging in the information that we have for this star, we end up getting a distance of roughly 955 kiloparsecs. Now, this completely overshoots. This completely overshoots, of course, the distance for the Andromeda galaxy. And if I'm not mistaken, this distance isn't even within the Andromeda galaxy. But of course, this calculation is heavily dependent upon the values that I'm using for the apparent and absolute magnitude. Of course, I believe now the 31.4 days seem to be kind of like a solid period for this particular Cepheid variable. However, as I quickly read through the paper, like I'm telling you guys, like I tried to blaze through the paper because I knew I wanted to get this done before our stream. I saw a bunch of different. I've seen a bunch of different apparent magnitudes quoted for this Cepheid. I think it was almost even as high as, in this case, as high as 18. So when I say as high as, when I'm referring to magnitudes, the magnitude scale is not intuitive. And what I mean by that is the higher the magnitude, the dimmer the object actually is. So 19.4 is a dimmer object compared to an 18 point something object. But guys, essentially that's the as far as I'm concerned, that's pretty much what I wanted to cover with talking about these Cepheid variables. They're one of the many tools that astronomers can use to determine distances from us to other locations in our universe. I think they're useful as, and you can look this up actually. The distance, it's called the distance ladder. They're useful for being able to determine distances as close as, like, I think around on the kiloparsec scale, all the way out to about, I think it's a few tens of megaparsecs. Beneath that, or lower on our distance ladder, you'd want to use parallax. And if you're using parallax, you're probably definitely determining distances to objects that are within our galaxy. With this method, you can determine distances that are extragalactic. So, very useful method. And there's, of course, you go higher up on the cosmic ladder, distance ladder, you'll be able to see other techniques that you can use to determine distances to objects that are much farther away from than like a few tens of megaparsecs. So let's see. So Hanny is asking, how do they find single stars and other? So single stars, as far as I know, we can't resolve. Let me be careful. So we can resolve single stars in, for example, the dwarf galaxies that are nearby us. Our satellite galaxies, the Magellanic Clouds. We can resolve single stars. But as far as other types of single stars, these Cepheids, and I'm not even too sure we're actually resolving the Cepheid itself. We're just seeing the brightness of its light over some period of time. I don't think that we're able to actually zoom in close enough to see the Cepheid in other objects that are nearby it. So I think it's more so we're just able to see these periods of brightening and dimming from this being caused essentially by a single star. But I don't think we're actually resolving single stars though. We're just seeing its change in brightness. And there are other types of standard candles as well. For example, supernova type 1A are what's used also. Well, they're also considered standard candles as well. And a supernova type 1A is a white dwarf that has accreted mass to the point where it's past the 1.4 solar mass limit, and it undergoes an explosion. So let's see. Astro YYZ. So I observed a globular cluster in the large amount. So yeah, whenever you're talking about resolving single stars, you basically use I think it's small angle approximation. So the idea is that you have us, we're observing from Earth, and we have some distant object. To be able to resolve a single star, you'd have to be able to take into consideration the angular the you have to take into consideration the angular resolution of the instrument that you're using, and basically you compare that angular resolution to the angular size of the object you're trying to resolve. If your angular resolution is higher or is greater than the angular diameter of the object, you're not going to be able. Well, wait. Let me not say that. You might be able to resolve it. It heavily depends on your angular resolution. That's really what you want to be able to do. You want to calculate, well, what is the angular diameter of the object or objects that you're observing, and you look at it, I guess, on a pixel by pixel basis. Well, what is the angular resolution of a single pixel? And you try to determine, well, if the angular diameter of your object is bigger than the angular resolution of your single pixel, then you'd be able to see the entire object, of course. So Astro did. So it looks like Astro did a question mark for, yes, the Chandrasekhar limit is for the for supernova type 1A explosions. So what is AFK short for? But yeah, I'm now opening up the chat for questions. Yes, away from keyboard. All right. But essentially, that's pretty much what I wanted to talk about for today. I'm pretty sure I'm gonna, like always now, I always have problems with coming up with topics, and I typically come up with the topic like a few hours before the stream. So, but yeah, that's the topic for today. So how far away do these standard candles work? Well, for Cephied variables, they work on the order out to the order of a few megaparsecs. Not a few, but tens of megaparsecs. So you can observe out to relatively, well, it's like local as far as galaxies are concerned. On the scale of intergalactic space, it's kind of local. That is a very good question, Wilburster. So extinction, and so the idea here is you have an object, a distant object, well, not even distant, but you have an object away from us, and the light that comes from the object passes through stuff, and that stuff extincts, or essentially removes or diminishes or dims the light from the object. Um, And because of that dimming, it could throw off your calculations for distance measurements. That's a good question. I'm not too sure. I mean, so if we're looking at let's say we're looking at a distant galaxy, what we're concerned, of course, is that we have the inner. Let's say we're looking at an extragalactic Cepheid in another galaxy. What we're concerned with is the fact that that light has to pass through its interstellar space, then the intergalactic medium, and then our interstellar space. Um, but yeah, extinction is basically the dimming of light as it passes through stuff between us and the object, the source of light. But yeah, I don't know exactly or off the top of my head right now I can't think of exactly how much we have to consider extinction. I'm pretty sure it has to be considered to some extent, but I'm not too sure exactly how much it affects the calculation. So how do they know how far away the really small red galaxies in the Hubble Deep Field are? Um, that's another great question. So let me think. If you're not if you're not being able to use, of course, this technique to be able to observe those objects, you'd have to use one of the other distance techniques another technique to establish distance to the object. So redshifts, yeah, you can calculate redshifts to objects. Um, oh well, yeah, right. So yeah, you can use you can use Hubble's law, depending on and I can't remember exactly what range Hubble's law is best used at, but it's definitely used for like the more distant objects. But you can use Hubble's law to be able to calculate the distance to it, as long as you can calculate the radial velocity of the object relative to us. The equation I think you'd want to use is something like, I think it's CZ is equal to H naught times D, where on the left hand side of the equation you have the speed of light times the redshift of the object, is going to be equal to the Hubble constant, which is H naught, times the distance, which of course will probably be in units of megaparsecs, of the object itself. So Astro states, so accounting for lots of dust and maybe using infrared data too. Yeah, for the extinction, right? Thanks, Astro. See, guys, I love these. I was missing these conversations while I was at the retreat. It's definitely fun to be able to like have conversations about um, astronomy related topics, and then also be able to have conversations about the lunar science that me and Dr. Plazas and Dr. Pamela, and also you guys haven't heard, but my postdoc mentor, Dr. Jennifer Greer, I'm working with a few other people as well on this project, um, at the Planetary Science Institute. But yeah, it's great to being able to have these conversations. Um, oh, that's good to hear that you're able to take vacation. Vacations are great. Has anyone created a navigatable map of the universe with this? Oh, um, that's another great question. I know that this technique has been around for some time, and it's been used to be able to establish distances to other objects. But the key thing is this, though. I want to mention this. So earlier I mentioned the cosmic distance ladder, and typically whenever you establish, so for example, we've been able to some degree establish the parallax method of calculating distances. Well, to establish the next step in that ladder, you'd first use the previous step to kind of calibrate the next step in the ladder. So for being able to use Cephied variables as a distance as a means of as a standard candle to calculate distances to objects, we've been able to establish, of course, that period luminosity relationship using though the other technique before it, which is the parallax method. And then of course this particular method is used to establish other distance measurement methods that are higher up on the ladder. It kind of sucks you're not paid for it, but I completely understand that it's worth it. Nothing beats being able to relax, de-stress, forget some of your responsibilities in the world, and then come back to it eventually. But yeah, even while I was on the retreat, though, I mean, it was very relaxing. I was able to. So the retreat was in Tucson, Arizona, which is where the Planetary Science Institute is based. And while there, of course, I was able to sit in and listen to several talks on what's new in planetary science, what's going on in planetary science. Now, me, I have a background in high energy astroparticle physics. So sitting there listening to everyone talk about planetary science and stuff like that, it was a lot of it's all new information to me. But it was relaxing. I wasn't thinking too hard because I don't really know much about those fields anyway. But it was definitely fun. So I see a question that's popped up there. Did you use these a lot in your work? Use these Cepheid variables? No, no, not at all actually. So in for my dissertation, I did my work on studying ultra high energy cosmic rays. So actually, some of the questions that you guys were asking earlier to Andres, I was tempted to chime in, but I was like, you know what? I'm gonna step back, and he got this, and he answered the questions great. Um, so, but no, I didn't use Cepheid variables in my research. Um, my research primarily focused on, well, the main focus was on being able to detect ultra high energy cosmic rays when after they've interacted with a particle in our atmosphere. But I also did a little bit of work on studying the somewhat the source conditions and the propagation of ultra high energy cosmic rays from their source to us. But as far as Cepheid variables are concerned, they would not be considered a source of ultra high energy cosmic rays. So I didn't do any sort of study on Cepheid variables. Sterile neutrinos. Um, so I don't know a great deal about sterile neutrinos actually. I do know this though. Um, in the production of ultra high energy cosmic rays at their source, typically you end up getting a large production of neutrinos um, from the various particle interactions that are occurring. And so you can actually, if you have so given that information, if you've detected a cosmic, ultra high energy cosmic ray, and you also can see nearby in the sky that there's also a source of high energy neutrinos coming from that direction, it kind of gives you a sense of how to match the ultra high energy cosmic ray to a potential source. But as far as sterile neutrinos are concerned, I'm not too sure. I don't have much information on those. Aren't only one hand of neutrinos ever seen? Um, if I'm remembering correctly, there are three different types of neutrinos in the standard model. Um, the muon neutrinos, the tauon neutrinos, and the electron neutrinos. Um, is one preferred over the other? I'm not too sure. Or are there ratios that much different? I'm not too sure about that. No, I never did any work with the Large Hadron Collider or any of the colliders actually. Um, I was working with at the time I was a junior graduate student, and so for my dissertation I did essentially a collaboration with another school. So I got my degree from Vanderbilt University, and I was working alongside researchers at the University of Chicago on my for my dissertation work. And when I was during my like junior level um, graduate school career, I was working alongside one of the more senior level graduate students at the University of Chicago, and if I'm not mistaken, he worked at he did some work at one of the colliders. But no, I've never done any work at any of the colliders, unfortunately. You mean doing the collaboration sounds very complicated? It was actually pretty fun. I mean, every week, we'd probably have like a quick telecon every week or two just to give updates. Oh no, high energy physics. So that's the reason why we do these streams. Whenever I'm done with the stream, I just hope that I haven't complicated a topic more for someone. I want them to be able to go home and be like, "Hey, I can do that," because you can. Honestly, I mean, anybody can do the work that I'm doing if you have the patience and the yeah, if you have the patience for it, and also I want to say the love for it as well, you can do it. A lot of people are a lot of people stray away from the sciences. I think because of course they probably heard from someone saying this is hard to do, or they also run into the situation of like I don't like math or something like that, and the science that I do is math intensive, but you can do it. That's one of the major points I want to put out there. They can be tough to read, but if you keep reading them over and over again, bit by bit, that little curtain that's hiding all that information, it begins to like move back, and you can kind of like start seeing what's going on behind the curtain. Well, Henny, I'm definitely happy that you find it interesting. But yeah, anyone can do what I'm doing. You just have to have the patience for it, and and to some extent a love for it. I mean, everything that I do in science, I don't like, not everything, but a lot of it I do though. There are times I'm very frustrated when I run into some math that I just cannot explain at all. Yeah, planetary science. I'm finding is it's a very fun topic to learn. I have no formal training in planetary science, so everything I'm learning now is just based off of hearing various discussions on the topic. I am so sorry to hear that, Will. Um, I so I for my first so calculus one for me was a breeze. It wasn't very hard at all. Calculus two, when you start getting into multivariable calculus and stuff like that, or is it multivariable? I think calculus three was kind of multivariable. Um, it gets harder as you move up, right? But if you stick to it, I think it depends on who's teaching it. One, it depends on also if you're able to get in like study groups. I loved study groups. It made the information a lot easier to digest. Oh, Hanny, you are so right. It's some types of math. It is very hard to turn into like words. I agree with you on that. Yes, study groups and office hours helps a lot. I agree with you on that. Um, but yeah, some math is kind of hard to turn into words. And other types of math is not so hard to turn into words. Okay. Yeah, I really want to actually get some teaching experience to kind of improve my resume. So, and that's one of the reasons why I enjoy our conversations, because when I'm trying to explain something, if you guys aren't understanding what I'm saying, you will definitely like say, Matt, that doesn't make any sense to me. What are you doing? What are you saying? What are you doing? Or if I make a mistake, you guys catch me on those things, and I enjoy that. Well, guys, the time is now 1:25. Thank you, Astro. The time is now 1:25. I really enjoyed our conversation today. I don't know if Joe's gonna be back with me on Friday. He might, but if not, that's cool. He's busy doing some other work right now. So I guess that's it for me. I'm gonna go ahead and sign out here and say thank you guys for joining. I will be back on Friday, directly after another episode of Daily Space, and so I will see you guys then. All right, guys. Bye.